With that, if I could ask the service provider panel to come forward with the title, Bringing Innovation to Life. We'll hear from a number of individuals and moderated by Jim Watson. Shane Collins with Oxford Performance Materials, Chuck Alexander with Solid Concepts, and Seamus Meagher with GCM. A little bit about Jim as he comes up to the podium. He's the president and CEO of the California Manufacturing Technology Consulting, which is CMTC. They have a broad-based mission as a nonprofit that focuses on creating solutions for profitability in growing Southern California's small and medium-sized manufacturers. Serving over 700 manufacturers annually, CMTC provides a broad range of services for innovation and growth, energy efficiency, continuous improvement, workforce development, and supply chain optimization. Jim.
Good afternoon. It's always great to be on after lunch. I'll keep hitting the mic. That'll kind of wake you all up. My background is totally manufacturing. I'm not on the development side, just so you know. By the way, how many manufacturers are here? Please raise your hand. Wonderful. By the way, there's no tax implications if you raise them, so all of you raise. I don't know about you, but I think there's two areas that, to me, jumped at me all morning, and that is of what this process can do for manufacturing. One is speed to market, and the other is failing fast. And while it's probably old news in this room, it's probably something that you all already were new when you came here, but for a majority of manufacturers in California, in the nation, they don't know anything about additive manufacturing and how it can take them to market faster, and how they could, and if they do have a problem, how they would fail faster. And as you know, speed to market is one measure of how competitive you are in the global marketplace. And so additive manufacturing, if we could expand it to more manufacturers, could really, really increase our global competitiveness of California and the nation. And second of all, the idea of failing. You know, I came from manufacturing. We never failed fast. We always failed expensively. And along with failing fast comes fail cheap, okay? And for a small company who is risking every time they put a new product in the marketplace, their very company, failing fast and failing inexpensively is the difference between life and death for that organization. So today, if you were a manufacturer, where would you go to get help? And this service provider panel is really designed as examples of organizations that can help manufacturing if they want to move into the additive manufacturing arena. And our panelists are Shane Collins, who's doing double duty for us today. Thank you very much. You know about him. We now have Chuck Alexander from Solid Concepts. Chuck, raise your hand. Mr. Alexander joined 3D Systems as an applications engineer in 1989 and quickly advanced to a product manager of 3D's then Vanguard SLA 500. Mr. Alexander joined Solid Concepts for 18 years as the P&L manager for the additive manufacturing department. Chuck recently returned to marketing at Solid Concepts as the product manager for additive manufacturing products. Probably a much better job than the one you had with P&L, right? A lot more fun.
It's different.
Our third panelist is Seamus Meagher, president and CEO of Global Contract Manufacturing. GCM started additive manufacturing in 2010 to support customers with product development as well as improve manufacturing communications and speed. Since acquiring this equipment, they have used it routinely for new product visualization as well as soft fixturing, component manufacturing, and product development. So we have a good panel here today. These are examples of how manufacturers can get help. Hopefully we'll have a lot of questions after the panel as to how that process actually takes place. So how do I pull up the first presentation? Where am I?
You're good here.
Good there?
And we have Shane.
All right. Why don't we start with Shane?
So I get to do my own presentation now, which is always a great benefit. And I was glad to hear that the National Additive Manufacturing Innovation Institute, the NAMI facility, was mentioned earlier. Our company, OPM, will be one of the first contracts that was awarded from the NAMI. We're going to be doing the design allowables for a material very similar to this for the F-35 in order to put parts on the Joint Strike Fighter. So we're very happy to have gotten that in conjunction with Northrop Grumman out of El Segundo. and we will be developing the B-basis design allowables so that people can design to that. So Oxford Performance Materials, we are, on the one hand, we are an OEM in that we manufacture medical implants using this PEKK material. It's FDA approved. Last week we got our 510K on the first device, which is a cranial implant. And we'll talk a little bit more about that. So we know what it's like to be an OEM. We're also the, well, service bureau, service provider. We don't really like those terms anymore because they're not really descriptive of what we do. We're a contract manufacturer. So when you're on the high-end applications, I think that's a little more applicable rather than someone who has maybe a couple of 3D printers and they make some prototype parts that get used for concept models. Those are great applications, but what we do has a lot of certification required, and it's more of a contract model. We're also vertically integrated into making our own materials. So before we had the FDA approval process for the custom cranial implant, we had our materials being machined into spinal cages and other FDA approved. So we're vertically integrated. We have the materials, we have the process, the machining, the additive manufacturing with laser sintering, and then we also have our own medical devices. So we started at the top with the cranial, and the plan is to go right the way down with other FDA-approved materials. So let's talk a little bit about the material itself. It's PEKK. It's a cousin to what you may have already heard about PEEK. It's a high-performance polymer. It has really good performance in that it has really good resistance to any type of solvent. So the corrosion resistance is very high. It has very high melt temperature relative to other polymers, so it can be used in a lot of really hot applications where conventional plastics can't be used. And it's also biocompatible. So it's a wonder material. What makes it different from PEEK is this small chain here. But because of this, the way that it's put together, we can customize the material based on the application. So we can make an amorphous version of the PEKK material, which has translucency and works really well for films. Or we can use the semi-crystalline form, which is what we have to support the laser sintering process. So within our organization, we have, as mentioned before, the OsteoFab. The OsteoFab is our process to make implants. But in addition to that, we can make industrial parts, such as what we will be making for the Joint Strike Fighter. We also have the raw materials. And then as a need to be able to take these cranial implants and figure out whether or not we actually made it to the model from which it was designed, we had to develop our own metrology sciences to be able to do the inspection. So as additive manufacturing becomes more widely used, we'll find that these organic shapes that can be created pose problems and difficulties in doing some metrology and measurement and quality control. So with this scanning technology, we can quickly verify that the skull implant that we made for this individual fits the model and is going to work in the surgery. So modern implant manufacturing, and I think what is going to be the future, and anyone who's had a major hip replacement or a knee replacement can appreciate the invasive nature of major implant that's done. Traditionally, the approach is that it's a one-size-fits-all, sort of. I mean, there are some different sizes. There's left and right. Could be female and male, but generally, they're not all that custom. And so the outcome of the surgery varies widely. One leg, you could have both legs done. One would be very painful. The other is a quick recovery. So I think what we're going to see in the future of the implant is that we will have a CAT scan that will allow us to know how to make the implant exactly to fit right the first time. So we have two data imports, MRI and CAT scan. They will be reconstructed and are reconstructed with some type of software that will allow us to threshold through the tissue we don't want to see to expose the areas that we're looking for. That will create a model from which a negative or the actual implant itself will be derived. So there's this whole design aspect. Once you have the design aspect, you can branch off a couple of different directions. You can go to a metallic implant. You could go to a polymer implant like from our PEC material. You can also go the direction of cutting guides and surgical guides so that the surgeon can have a better outcome. And I think those were mentioned earlier. So the key is having the right input, and then the rest can follow through. So this is the general approach. So this is exactly what happens. You see that you take the CAT scan, you've got a void, you determine what the size of the implant will be, model that, and I would have liked to have had a nice case study, but it couldn't get released, so we're being generic here. But what we're showing is, in this case, this is an acetabular cup for a hip, where we have the osseointegration network structure, where the bone can grow into, being designed along with the implant itself. And we see that quite often in the implants. So now we have the design, we take the material, we add it to the machine. In this case, there's only one machine manufacturer in the world that can make this. It's about $1.4 million a copy. So you can see the issue with expanding that. And then we have the metrology system for the quality control. So in closing, OPM is a company that has integrated vertically by necessity to be able to make sure that we have FDA approval of the entire process chain, from the materials to the process to the quality control. And in the LA Times a couple of weeks ago, there was a story about an implant we did 2 weeks ago where a man in New York had 75% of his skull replaced with one of these implants. So thank you very much for your time. Now we look forward to the questions.
Thanks, Shane. I'm getting to the age where I'm really going to watch his website closely on replacement parts. So keep up the good work. Next, I'd like to ask Chuck Alexander to step up from Solid Concepts.
Thank you. All right, I put my slides together, and I went right to a case study that I'd like to go over with you, and realized that I didn't put anything in there talking about Solid Concepts, so I figure I better spend a little bit of time so I can get my expense report signed when I go back. Solid Concepts, we are the largest dedicated contract manufacturer using additive manufacturing equipment, process, and materials in North America. Last year, we exceeded $62 million in business. About half of that was additive manufacturing products. We have 77 pieces of additive manufacturing equipment that we use. And so I guess the point of that is that there's 2 points. One is that we're headquartered in California, and 3/4 of our manufacturing capacity and our employees are located in California, down in Southern California. And the second point, which just escaped me, is that additive manufacturing is a manufacturing process that we've been utilizing for over 20 years now. And so everybody who's new to additive manufacturing, you're kind of in the second wave. And I used to call it a second generation of additive manufacturing because I've been doing this for 24 years, almost a generation. But it's really not a second generation. I think additive manufacturing, what we're looking at is we're really getting to the adoption phase of the technology. So we're past the acceptance phase. We're past the early adopters. And so I think in 2011, additive manufacturing as an industry was an $11 billion industry. So if we're just now getting to the acceptance phase, I think that might answer a few questions as to how this could change manufacturing. All right, so I picked an example here, case study, and this is using additive manufacturing for a flying part in an airplane. This happens to be the latest story we can tell at Solid Concepts. We're under NDA for most of our contracts, so we can tell one out of 1,000 stories that go through our shop. What this is Orbis International has a flying hospital. Currently, it is a DC-10 that they fly, and what they do is they fly around the world to do eye surgeries for people who are blind. Now, Orbis says that of the 39 million blind around the world, 80%, or nearly 32 million, suffer needlessly. And so the DC-10 that they had was out of date, and so they had a project where they got a donated McDonnell Douglas MD-10-30 from FedEx, and so they were looking to make a new flying hospital. Now, the purpose of this flying hospital is not only to do eye surgeries, but also to train eye surgeons. Along the vein of not only giving a person a fish, but they're teaching people to fish, or in this case, do eye surgeries, is a secondary purpose of this flying hospital. The reason why they wanted to upgrade the plane was that they would be able to design their hospital with a new modular design. That would allow for reduced maintenance costs so that the hospital can be basically removed from the plane to be maintained or replaced. Also for increased performance of the plane, fewer fuel stops for fuel efficiency. Also, it allowed them to land at more airports around the world, so they were able to cover a wider area. And then reduced operating costs by having fewer pilots, reduced maintenance, and then the fuel savings. And also, they were able to increase audio-visual capability, which goes along with their training mission to train surgeons, where they can broadcast and go out over the internet to make the training available as they're on site. So why did they come to Solid Concepts? Well, the airplane, as you can imagine, used for FedEx is almost a completely bare plane, a lot of cargo space in there, perfect for building a hospital in. And the requirement that they came to us for sounds pretty simple. It was an air conditioning duct, basically, to move filtered air into the operating theater for this particular flying hospital. But the requirements of this duct were such that it was a complex shape. Ducting is a big application for additive manufacturing as far as production applications or parts that actually go on customer product. And ducting in a lot of applications, automotive and aerospace, is that the people the people who design the ducting that goes in the airplanes and things, they're usually at the end of the design cycle, and so what they get to do is put their ducting in the spaces that are left over after all the other systems people have gone through to put in whatever it is that they have to put in. So this duct that one of our marketing assistants is holding here is a piece of ducting that had to go around some structure of the airplane, and so it was fairly complex. Now, also, the duct had to meet all the FAA certifications because this is commercial aircraft, so it falls under the rules of FAA. And so the material had to, that we used had to meet flame, smoke, and toxicity ratings. Also, the part, because it was flying on commercial aircraft, had to be certified for airworthiness. All that while performing the function of the part and remaining lightweight. So when Orbis came to us, Solid Concepts, what they originally had in mind was that they had a duct and they were thinking, well, normally these are done with fiberglass layups, things like that. So that's kind of a cost point that or a price point that they had in mind when they started talking to us. So one of their first questions was, well, yeah, this is great stuff, but how much is it going to cost? And so we ballparked them, and then we picked them up off the floor and put them back in their chair. But going through the process of talking about the manufacturing and what additive manufacturing could do, what it allowed for was we found out that the particular design of this duct wasn't final yet. They weren't quite sure where it was going to be routed. And so there may be iteration in this duct. And it turned out that there was iteration for this particular example. So doing a fiberglass layup, okay, well, are you going to have to make a second tool to do a fiberglass layup? You're going to have to modify the tool. So we started to add things up. Fiberglass sounds cheap until you start adding in all of the things that you have to do for the process. Something else that we talked about with additive manufacturing, one of its primary benefits is that you can start to combine parts together. So mounting bracketry and other elements, wiring harness holders, and a lot of things can be modeled into the geometry with additive manufacturing, where you can reduce part count and reap those benefits as well. So once we went through that process with the Orbis engineers, they started to realize the real costs of things and how additive manufacturing could save them some money. So they decided to go down this road of making this particular duct with additive manufacturing. Now, Solid Concepts, we have a number of different additive manufacturing processes. We have 6 of them. And so we quickly had to zero in on which processes we were going to use to make this duct. And there were really only 2 processes that were viable. One was the SLS process, which is the powder process where you add IR energy to melt the powder layer by layer. And the other was the FDM process, which you've heard a lot about. That's the extrusion process where you're extruding different types of plastics through a nozzle and laying that down layer by layer. The reason why those 2 processes were the only viable ones is because they were the only ones with materials that would meet the FAA specs for flame, smoke, and toxicity. We eventually settled on FDM because the SLS process, one, wasn't accurate enough for this large of a part. It's a 3-foot long duct that's about 24 inches in diameter. Also the material cost for a part this high, or this large, was very high for SLS. So FDM was more economical. So the end result of all of this is we went through a couple of iterations. One was a prototype duct that we built. They decided to change the design. And what we ended up with was an FAA certification for airworthiness to fly this part on the hospital. We don't know for sure, but we think this is the first part that's ever got an FAA tag for airworthiness to fly on commercial aircraft. Now this particular part, because it's a one-off, it was qualified as a prototype, so that probably helped it get through the airworthiness rating here, or the certification. So, but we are involved in projects where more testing is being done so that we can tag parts in a production mode using additive manufacturing processes. So a great success story. Thanks for your time.
Well, manufacturers in Southern California have already gotten a valuable dividend out of this forum because now we're aware of Solid Concepts. I'm sure that CMTC and Solid Concepts have been operating in different orbits, but now we have a resource that we can work with as we begin to ferret out manufacturers in Southern California who are interested in growing their businesses. We now have a resource to go to. So, Seamus, you're up next.
All right, thanks, Jim. Happy to be here to talk a little bit about global contract manufacturing. So we are a subtractive manufacturer. We spend all day long, feeds and speeds, trying to remove metal off of material. You probably wonder, what am I doing here? Today I'm going to talk a little bit about our company, what we do, and then how additive manufacturing, or really for us 3D printing, helps our company. In Union City, California, about an hour away, we have 140 employees. Again, we're doing manufacturing services. So we're building to print for customers on an everyday basis. Picture there of our facilities. This is the equipment that we acquired in 2010. So it's a basic 3D printing piece of equipment. You know, at the time, we were very interested in additive manufacturing for prototyping, for working with customers on developing their product, value engineering. So we purchased this equipment at that time. Just a quick show and tell. So this is an example here of a part that we made out of ABS plastic. This is what the customer wanted. So you can see this is hogged out of a billet of aluminum. Why would we print it out of 3D? I'll get into it in a minute here. Here's really the applications as we see it for us. When we get a complex product to manufacture, one of the first things that everybody wants to see is a sample. Of course, if it's never been made before, no one has a sample. So what we can do with our 3D printer, within hours of getting an order for something like this, we can start printing it. So the next morning, we have a 3D sample. And how is that useful? Well, most engineers, if they look at a part on a 3D model on the screen, they may not be able to figure out the most optimal way to make that part. But if you print a 3D model, you can really noodle around all the different ways to hold it, to clamp it. You can give it to people in the manufacturing facility who don't have 3D capability. They're not an engineer, they don't know how to use SolidWorks, but they may have valuable input on how to make that part. The next thing we do is we can take it into our inspection lab, and because a lot of the customers in Silicon Valley need their parts in only a few weeks, we can take this to our QC lab and we can start validating our coordinate measuring machine programs for quality validation. At the same time, we can be working on this. At the same time, simultaneous to that, the guys in the shop can have this as feedback tool for our engineering folks to say, you know what, we're having a problem down in here, we're having a problem over here. When you bring this into the engineer and tell them that on your CAD/CAM program, that's much more effective. So that's a number of the ways we use this product. We also do it for making fixturing and components for different customers. This is an example of a fixture, electrically insulated. It's for some contacts. Rather than make it out of some other material, we just printed it, and we're done. Also, for some low-volume components, we've had customers that only need a part out of ABS, and it's not that tight tolerance. We can just print it. So we also offer it as a service. If anyone's interested, you can come see me afterwards. This again is the example we talked about. ABS model here on the right, the part over here on the left, and see our shop out there in the background. All right, that's how we use it. Thank you.
Okay, time for questions. Do we have any questions from the floor? None? Well, being a good, I'm sorry? Oh, is it on? I think you're alone.
Working? Good. Yeah. I like the idea of creating the rapid prototype right off the bat for a complex machine part. Have you ever taken it farther and created miniature models of much larger systems for that kind of a communication?
We haven't. We've done the opposite. We've taken very small parts and scaled them up. So for a specialized furniture fitting manufacturer, we took some parts that really conceptually they couldn't visualize. We actually scaled them up to larger sizes. But you can do the same thing.
Yeah.
Yeah.
Great.
So scaling is an important technique that you can use with a 3D printer.
Thank you.
Can you tell us what that thing's for?
What thing?
Bill. Any other questions? Oh, yes.
The gentleman with the PEC material, is that available in pellet form for injection molding as well? I went down the path on another ink project with implant grade ink that can't be purchased in pellet form, so I can't migrate that platform to injection molding when it goes into volume.
The question is whether or not the PEC material is available in pellet form for injection molding. The answer is yes.
Question over here.
One question for the medical processes. The machine you mentioned was 1.4 million. Who makes that? And then what sort of tolerances are you getting on that machine? What's required for medical purposes?
The question is who makes the machine and what are the tolerances that we can get from the process. The manufacturer of the machine is EOS of Kreiling, Germany. They're the only company that commercially makes a machine that can process laser-centered, high-temperature materials in the melt temperature realm that's necessary for this process. The tolerances, and I'm going to give the stock answer that Chuck will appreciate, depend on the geometry of the part. So that's my way of getting out of having to answer that directly. It's a thermal process, and there are a lot of factors that go into what kind of accuracy you can ultimately get from the part. And generally speaking, the tolerances have to be opened up the larger the part is. So if you're making a really large part, the tolerances have to be obviously opened up over a small part. The other side of it is that we like to make the part more than once to be able to get the parameters set dialed in for that particular geometry. And in a production environment where we're making these cranial implants, we get those to within a few thousandths of an inch, probably 2 to 3 thousandths over a fairly large size, because we know that they're going to be all within the same sort of general size. And you can dial in the parameters for that.
Just another comment about accuracy is that you know, we have a lot of manufacturing processes. We also have a fair amount of CNC equipment and things like that. So we hybridize manufacturing technologies and techniques all the time, where if you need tighter tolerances, those can be secondary operations where you're machining and things like that. And so, you know, someone mentioned this morning, you know, the additive manufacturing isn't a replacement. It's really something different. And if you approach it as something different and look at the benefits and things like that it provides, you usually don't see the obstacles then. You see where you can use it and where it can go. So this second generation we have, I think sometimes, you know, I know that I get stuck approaching things from a traditional manufacturing viewpoint, even though I've been using additive manufacturing for 24 years.
I have a question for you on the ductwork that you showed. Was that one machine run, or did you glue parts together to create that?
That part was built in a single piece. So that was another reason to use the FDM process. The machine that it was built on, it was a Stratasys machine, the Fortis 900 MC. It has a build envelope of 3 feet by 2 feet by 3 feet. So it was built in a single piece.
What was the wall thickness?
I think it was around 1/8 of an inch. That's what I think it was, but yeah.
Bill?
Seamus, what would be the tipping point for you to go to a sintered metal machine versus just a plastic machine?
That's a good question. I've been looking at those at the tool shows, and we're always interested in that. But I think we need a client base that really needed that. What we're seeing is that most of the people that need a laser sintering are going to buy the machine themselves and do it. So they probably wouldn't do it as a manufacturing service. So that's what we're seeing.
Strategy into the rest of your business, or do you see it being a standalone prototyping business as well? And have you had clients where you're just doing rapid prototyping for them? They're going to do something else with the model?
Yeah, for us, we see it as a support process for the CNC machining and the traditional manufacturing techniques. Naturally, we can see some evolution that may cause us to get more engaged in that technology, but for right now, it's a support process, and we just look at it as another tool in manufacturing of many other different types of processes as well.
There were some talks here about the threat to traditional manufacturing from the rapid prototyping or advanced manufacturing processes. Do you feel that threat?
I'm sorry, could you repeat that question?
There was a conversation here that the advanced manufacturing or additive manufacturing will be replacing traditional machining, CNC machining, and do you feel it as a threat or not? I mean,
no, I don't. That's a good question. The question is additive manufacturing a threat to traditional manufacturing? And I think about that, and I would say no. If you look at a lot of, for very small parts, I think it's definitely you know, a threat to some of the traditional manufacturing technologies. But if you wanted to make a large part out of 3/4 inch steel that's 5 feet by 4 feet, I guarantee you a steel mill can roll it faster and I can cut it with a laser faster than you'd ever do it with additive manufacturing. So, you know, there's a place for every manufacturing technique. You look at the screw machine technology now, and metal cutting technology in general has gone through a lot of evolution too over the last 20 years. And I can make a very complex screw machine part for $7 in about 60 seconds. So I say there's still a place for the metal removal folks. Thanks.
Any more questions? No? Shane, Seamus, Chuck, thank you very much for the panel.